Once again, I am sending around a sign-in sheet. Please sign in. I want to continue our descriptive statistics discussion. We were looking at variance, standard deviation as measures of spread related to our idea of average. And I said there were two versions. The two versions end up with two different ideas based on whether we are looking at the population or at a sample. Now, this formula as written, rather unpleasant, is really the result of doing several steps. What we're doing is we're looking at the absolute deviation, the difference between each number and the average. We're squaring that. Summing all that up, that is the total squared deviation. We're dividing by n minus 1. The reason for the minus 1 is because we are dealing with a sample. A mathematician by the name of Bessel said that the sample could be biased. We could get a sample that is tighter together than our overall population because outliers are hard to come by. If you have a lot of outliers, then you'll get a wider standard deviation, but still they are outliers. They are rarer occurrences in our data set. So Bessel said, let's widen, because we took a sample, we might have missed some of these things. In a population, the only difference is the denominator. Now, the symbols change slightly because when we deal with a population, we're dealing with parameters rather than statistics. So we'll use Greek letters in a couple of places. And because we're dealing with the population, we're going to capital N. That's everybody. Now, since the variance is squared, the problem here is that we're going to get square units. If I'm dealing with dollars, this is in dollars squared. That doesn't make much sense. So it would be more useful to us to take the square root of this. That's our standard deviation. So what I'm going to do is I'm going to call the variance a squared object. For a sample, I will give this the symbol s squared. For the population, I will give this the symbol little sigma squared. So a lowercase sigma, a lowercase s, those represent our standard deviations without the square. When they're squared, they're the variance. So I could do all these calculations by hand. I don't think it's worth it. Here, are the two data sets that we were working with last week. You should open up Excel and type in these two data sets. But we calculated last week. These have the same mean. These have the same median. Mean and median for both of these sets is 5. So really, the way to tell them apart is based on their spread. There are built-in commands in Excel to do variance and standard deviation for both population and sample specifically. Sample standard deviation is denoted with an S, population with a P in the command in Excel. So in this block on the left, A8, I'm going to ask for the sample standard deviation. The command is STD, and as soon as you start to see it, they start to come up, standard deviation, DEV. If I want the sample one, it's .s. If I want the population one, it's .p. And then I just need to tell it what the data is. What a name. Oh, I hit an extra dot. I made a typo in my formula. You see, I have 2 periods in the formula. That's why it gave me an error. There we go. It gives me 1 billion decimal places. I really don't need more than 3 or 4. Most applications, I can just get away with 1 or 2, depending on what I'm going to do with it. So this standard deviation is 1.8. I don't know what these are measured in, so I don't know what units these are in. The variance can be retrieved by typing equals VAR. And then we see again, there's a population and a sample version for that. I rarely use variance on its own. I far more often use standard deviation. There are places in probability and statistics in general where we don't just look at one type of data. So instead of one variable, I've got multiple variables. And then we can talk about variance as relates to each other. More on that later. I'm not going to bother with the variance here. I just wanted you to know it exists. What's the variance for the other group in column C? Before you calculate, do you think it's going to be bigger or smaller? Why? The range of numbers is larger in column C. And if the range is larger, they're more spread out. I would expect a larger standard deviation, I hope. You can just copy the formula over from column A to column C, if I can hit the right button, and we do see it is substantially larger. Instead of 1.8, I now have 4.1, rounding. These both assume that these are samples taken from larger pieces of data, larger collections, because I used the .s version of the formula. What if you use the .p? Hang on a second. Before I calculate, if this is everybody, and I do the population standard deviation, should the number I get in this next cell down be larger or smaller? I'm using the exact same data. Looking at the formula we wrote down, which fraction should be larger or smaller? Felix? Right. Okay. If I divide by a bigger number, the bottom goes, the whole fraction should get a little smaller. Yes, because I'm going from dividing by n minus 1, in this case that would be 3, dividing by n itself, which would be 4, dividing by a bigger number, my fraction is going to get smaller. So if I write standard deviation dot population for the same set of data, it's smaller. It's smaller regardless of which data I'm using. It's decreased because I'm dividing by a larger number. In this case, a substantial amount of difference occurs. Dividing by 3 instead of 4, it's a big change. Dividing by 101 as opposed to 100 isn't going to be as big a change. So it is rare that we will make a big deal over which one we are using. It is your call. Again, on our Canvas page are a few examples. Under Module 2, go to the document that says Lecture 8. Let's take a look at some of the examples available to us. Here is the document file. Copy and paste these into Excel. Let's see if we can do all of these calculations. Yes. Lecture 8 document. Hey, Ben, where is that information? It is. Remind me, please, what is the range of our data set? Not the actual number we get for this, but the idea in general. What does range mean? Yes, it is exactly the difference between the largest number and the smallest number. So the easiest way to calculate that is What's the command I should give to find the range in my data set? I mean, this is a small enough data set I can do it in my head, but
So, check.
equals sum of what values, and then what do I subtract?
Now, put the largest and then subtract the small.
Ah, command to find the largest minus the command to find the smallest. What are those two commands? Exactly. So equals the maximum of my data set minus the minimum of my same data set. Notice that as I am beginning to highlight the second time, it highlights in a different color. It isn't until I complete that it knows, oh, you're using the same thing, so it makes it the same color. Excel is nice about color coding for our ease of identifying which pieces in the formula go with which pieces of data on our spreadsheet. And yes, the highest one here is 150, the lowest one is 90. Perfect. Range is 60. Variance, I said earlier, dot VAR, and then we have a choice, population versus sample. I'm going to do them both. I'm going to start with the sample. By the way, grab your phone or your calculator. Square root of 530 is square root of 530 isn't 23. I done effed something up. Because that's the only difference between variance and standard deviation. Variance is squared. Standard deviation is the square root of the variance. If I did population, var dot p is on type. It's smaller because we're dividing by a bigger number. Same thing with standard deviation. It's smaller because we're dividing by a bigger number. Questions? There are 4 different data sets in this set of notes. Let's keep going. Do the next one. when I compute the variance and standard deviation for this data set, I find that the standard deviation is a more useful measurement. Why? Regardless of whether I am doing the sample or the population standard deviation. Why is that more useful than this? Why is having a variance of 92.5 not all that helpful to me to explain variability to someone else? I don't have any numbers in the range of 92. Exactly. These numbers are all between 15 and 40. What is having a variance of 92 telling me? That's and the bigger problem is, what are the units for that 92? It's the same unit as our data, but squared. So 92.5 tasks completed squared. What the hell is a task completed squared? That is a useless unit. So I find it absolutely unhelpful. But standard deviation is in the same unit. 9.6 is the variation in tasks completed. Not squared, just tasks completed. Now, clearly some individuals here have a larger variation and some have a smaller variation from whatever my average actually is. What is the actual average of this data? I don't have that at the moment. Oh, okay. The average is 25. So, the median is 25. The average is actually 26.
Oh, sorry.
Okay, my apologies. So 26, I can think of the way my data would look on a number line or in a histogram or in some other sort of visualization. I can say, oh, the fulcrum balance point is at 26, 9 lower, 9 higher is where? I go up to 35, technically 35.6, because I add the standard deviation, and I go down to 26.4 if I subtract one standard deviation. That region should be a lot of my data. The further out we get, the less and less data should appear if I think in terms not of absolute number gaps, but in terms of the gaps being defined by my standard deviation. Frequently, we'll draw a number line, our average in the middle, and we'll mark off intervals in terms of the standard deviation, going both in the positive direction and the negative direction. And then ideally, I would have some sort of visualization that I could put my numbers on here, whether that's a histogram, a dot plot, all sorts of other visualizations we can create. I can then say how much of your data is in here between one standard deviation down and one standard deviation up, or here, 2 on each side, or 3 on each side. And depending on what I know about my data or the population my data comes from, I can make assumptions about what that picture should look like. Then, since at this point I'm just describing the data, I won't be able to draw conclusions from that. But as I go on, I will be able to say, oh, if I make this assumption, what conclusions can I draw about the sample I got? More on that in a little while. Questions? One more. Huh. In this set of data, I've got an average of 145 and a standard deviation of about 103. I'd really like to describe a little bit more than just this is how wide or narrow my data is. So now that I have this piece of information, what else could I do to describe the way this data is laid out relative to that average? I could describe, as I said earlier, the way this data is distributed across a number line. How am I going to visualize that? I could put up that number line. I could put a dot or a box plot or some sort of ranged histogram. I find all of these easy to do right here in Excel. If I highlight my data range and I go to the Insert tab, I can insert a chart. Matter of fact, there's a set of recommended charts up there. Right there. We can get a lot of stuff, right? I'm not all that thrilled about the charts they're providing me here because there really isn't any sort of number line relationship. If I create this column chart, it's showing me how big they are compared to each other, but it isn't really showing me where the data lay across a number line. I think I'd be better off with a different sort of visualization. What if, instead of creating that chart, I divvy up my information into ranges? Get back to the data in a minute. Frequency distributions and histograms. A histogram is a visual for a frequency distribution. So I'm going to start with this frequency distribution idea and then build the picture that goes with it. The first thing I need to do is to decide on how I am going to range my data. So depending on the data values I have, I'm going to figure out what sort of buckets I want to put them in. The dollar figures we were just looking at went from 50 to 300. Let's run with those numbers for a moment. I've got numbers from 50 to 300. I need to figure out how big bucket I'm going to use for each pile of data. If the buckets are too large, then I will just have a couple of pieces of values. If they're too small, then it'll be really spread out and the data might not look very helpful. For example, I could say I'm going to create the number line and I'm going to put every single number from 0 to 300 on here, and I'm going to put a single dot wherever one of my data values shows up. So we had a value at 50. There's nothing, there's nothing, there's nothing. Right here at 50, I put a single dot. There was a number at 75. There was a number at 100. There was a number at 200. There was a number at 300. Well, that's a little more useful, but these data are fairly spread apart, right? If I then add my average and my standard deviation, I could get a feel for this, right? If data appears in larger piles, this might not be the best idea, not having each and every single individual value. For example, if I give an exam to a room of 30 students, I'm going to have numbers between 0 and 100. How would you group numbers between 0 and 100 for grading purposes? I could do it in tens, couldn't I? And if I did it in tens, because 90 to 100, 80 to 89, 70 to 79, those correspond to letter grades, that might be useful to me, right? I don't know what the utility of breaking everything down individually would be. I could do it by single point. Who got a 99? Who got a 98? Who got a 97? How many of those do I have? Yes? But if I group them, I create a set of bins. In this example, grades on an exam, I've got values between 0 and 100. I could create bins of width 10. Now we have to make a decision, because ideally my bins should all be the same width. They should contain the same number of possible values. If that's true, then I don't want to go from 90 to 100 and 80 to 89. Why? If I put down a bin and it takes all the grades from 90 to 100, how many possible scores are in that bin? Count them out. 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100. That's not of width 10, that's of width 11. There are 11 scores available in that bin. Uh-oh. Now, if that's what I tell myself, I want a bin to have width 10, I have to make a decision. Do I go from 91 to 100? Or do I go from 90 to 99 and make 100 the next bin? Most of the time, that decision will be made kind of like our stem and leaf plot, right? Where we think about the first digit being a 0, the first digit being a 1, first digit being a 2, all the way up. Now that gives me a bin that is fairly weird, because the highest grade on this exam was 100, but I have a bin that goes from 100 to 109. A low bin limit and a high bin limit. And then I could just ask you to count how many are in each bin. If I've got 30 grades, the numbers I put as a count here should total up to 30. If I had 150 people take this exam, then my total should be 150. But I should be able to count how many are in each bin. I'm hoping these bins are very sparse. And these bins are much higher. But I don't know until I look at what's going on. If this exam had the majority of students do pretty good, what would you expect to see here? Numbers and values up at this end, numbers and values down at this end. Felix? These should be pretty high. These should be hopefully 0. I don't want anybody to score 7% on my exam. That means I did something wrong or they are a brick. I don't know. It's happened to me before. I have been in higher education for 30 years. God, that sounds so scary. And I have had students earn single-digit grades on exams. I still believe that those students were in the wrong class and chose not to withdraw for whatever reason. I am not the student. I cannot tell you what's going on in their head. It took until fairly recently for me to actually have a student earn an exam grade of 0. I had somebody show up to a final exam in a course. Final. Sit down, finish the final in 15 minutes. Do you know what they did? In each of the questions, they took whatever the first example equation that they ran into, they just wrote that equation down and walked out. That student earned a 0%. I've never had that happen to me. But clearly, they were going to be up here when most of the class was down here, right? Majority of that class did pretty well. And then there was that guy. Whatever these numbers are, and I'm going to make it up. Something like this. I could then make a bar graph for this. That result is called a histogram. This is my frequency distribution. I can now create a histogram. And because I have all of these bins, I would get a height of 1, a height of 5, another height of 5, a height of 6. I'd still have that height of 1 down here. There'd be a 0 there and a 0 there, and whatever else is in between, right? I'd get a series of columns. When I think about average standard deviation, I want you to picture things that look like this. Either a column chart or a curve that goes through the tops of these columns. So I could add to this picture some sort of curve that approximates the tops of all of these columns. That is our distribution picture, whether it's a bar chart, column chart, or a curve itself. Some of those curves will, over time, become more and more familiar to us because we'll use them in a bunch of different places. There's one of those kinds of curves. And now I can ask not just what does the standard deviation mean on this picture, but what else does this picture tell me? Standard deviation tells me how wide or narrow the cluster of columns is around the mean. A small standard deviation should mean a tight, high peak falling off fairly quickly. Now, units matter here. I'm dealing in grades. So small for a standard deviation here might be 12 or 15. A large standard deviation might be 20 or 25. If I am dealing with corporate revenues, which are usually in the millions of dollars, a small standard deviation might be $250,000. And a large standard deviation might be several million. So my units now matter to the way in which I interpret that word small. Questions? What do I do about brick on the end there? Okay. I'm going to add another descriptor. Actually, two, but they're related. Skew and kurtosis. I use skew way more than I use kurtosis. But these both really describe now more pieces of the shape. Rather than just narrow or wide, skew refers to lopsidedness. So skew I want to think of as a measure of either symmetry or asymmetry. The more symmetric our distribution is, the smaller the skew is. So if I have exactly the same number of things to the left side as I do to the right side of my distribution, or if I have the exact same width of columns on either side, that should have a skew very close to zero. The skew is positive or negative in the direction of outliers. My boy Brick over there is going to give me a left skew. If I were thinking of a curve, I think of the curve as having this long drawn out piece to get over to the left as having a left skew. Left skews, that's the negative side of the number line. That's a negative number. So we're really thinking of a picture fairly similar to the picture I showed you just a moment ago. That looks like this. Here's our histogram. And it's the same on the left and the right. That should be a very small or near zero skew. If it's longer to the left side, then I'm going to get a negative skew. If it's longer to the right side, I'm going to get a positive skew. I tend to draw curves more than I draw histograms. So I think of a roughly symmetric picture with its average in the middle as having a skew near zero. On the other hand, if there's a lot more stuff down there on the left, that should be a negative skew. Flip that picture over, left to right, and you get a positive skew. Yes, sir.
Skew is where the smaller,
Skew is where the longer tail is. So as I say, this tail goes out this way, this tail goes out this way. We can think of skew as kind of the reverse of where the big part is. So this bulge is to the right side, this bulge is to the left side. But it actually turns out that we can calculate a skew by thinking of the average versus the median. The very data sets that we did at the very beginning here. The mean was 5, the median was 5. Those were symmetric. They had the same number of things to the left of the mean as they did to the right of the mean. The same number of things to the left of the median as they did to the right of the median. One of them was further out, one of them was closer in, but there were 2 low numbers and 2 high numbers. So the mean and the median were exactly the same. That's this picture. That's zero or very close to zero skew. On the other hand, mean is sensitive to outliers and median isn't, right? So if I have this outlier down here on the left in this second picture, what's going to happen to my mean versus my median? In the case where we were symmetric, the mean and the median ended up the same. Mean is sensitive to outliers. So if I have a low outlier, it would shift my mean to the left. So the mean would be smaller than the median. So what should a positive skew tell me? Ideally, that the mean is bigger than the median. And in one sense, it is quite easy to calculate skew as the difference. Median minus mean. Mean minus median. That'll be a negative. That'll be a positive. But I actually have never calculated skew by hand, ever. Because if I want skew, I'm going to ask Excel to do it. Just like I asked for the maximum or the minimum or the standard deviation, I'm just going to say, go ahead, give me the skew. Questions? To give you an idea of how often I use kurtosis, I have taught probability and statistics physics, calculus, lots of other courses for 30 years. This is the first course I'm teaching kurtosis in. That's how often I use it. But what kurtosis measures is really the weight in my tails. That phrase should give all of you pause because you've been looking at these pictures for all about 5 minutes. And what do you mean the weight in my tails? I don't have a tail. Kurtosis tells me how likely outliers are. I could have a very large standard deviation because the data is spread out, but it's rarely going to be way outside. I could have data that's mostly clustered as a couple really big outliers. And those are different. If I asked you in either of those pictures to pick an X value under our curve, and I said, the chance of you picking a number is related to how tall that piece of the curve is. That means these numbers over here are relatively unlikely, aren't they? But these numbers over here are much more likely. Compare this tail to this tail. The tail in the second picture is much skinnier than the tail in the third picture, isn't it? That third tail has more weight. This picture has a higher kurtosis than this picture. More weight in the tail, higher kurtosis. Now, again, I don't use this idea very often, but when I think about a curve that is symmetric and nice and quote unquote typical, we'll talk about why this is the one we're going to use. It's called the normal curve. This curve, when I do the calculations, has a kurtosis of 3. That's kind of dumb. Why would the normal one have a kurtosis of 3? Well, it comes out from the way we do the calculation. I'm not going to give you the formula. It's too much of a pain in the ass. So frequently, you'll see a term that says excess kurtosis. If the tails are fatter than these tails, we're going to take the kurtosis and take away that 3. Fatter tails are going to give me a positive excess. Skinnier tails, less tail, is going to give me a negative excess kurtosis. Visuals, I need better visuals. Here are my skews, right? Longer tail to the left end, longer tail to the right end. My normal idea is middle kurtosis, mesokurtotic. I have never used that term anywhere. But notice how the tails are skinnier. Well, no, the peak is skinnier in that middle picture, right? But there are long tails. There's a lot of stuff that goes out there. Those are considered heavier or thicker tails. The chance of being way out, away from that center, because that's got a small standard deviation, there's a bigger chance to be out there than in this third picture. That third picture has a really big standard deviation, right? The data is fairly wide, but it cuts off. There's nothing to the left or the right, way out there. It's flatter, it's more spread, but it's really about those tails. I like to think of it as surprise. Remember, I said we were going to pick a value based on how big the bar was? This has a wider standard deviation. The chance of being further left than this leftmost bar, there's nothing out there. There's no tail to guess. In this middle picture, there is a chance to be further out. Those are rarer, but still possible events. It took me a while to understand kurtosis. I'm not expecting you to have this right away. I cheated. I asked an AI. Explain the difference between positive and negative excess kurtosis. Remember, I said above 3 was positive excess, below 3 was negative excess. Avoid using exact mathematical language. Aim to a high school business statistics class. And then here's some descriptions. But what it told me is that the idea of kurtosis is about surprises. When you have positive kurtosis, you could end up with a really low or a really high number more often because there's more tail, whereas everything else is clustered in the middle. When you have low kurtosis, negative excess, then it's really unlikely to get way out or way up. Market valuations, stock predictions, pricing design. I want low kurtosis. I don't want to suddenly be surprised by a huge loss or a huge gain. I want a nice, steady, low kurtosis in my market behavior, because then a huge bust or a huge boom is unlikely. But a steady behavior can be dealt with. I again posted a set of data for you. To compute skew, kurtosis. Here, in this set, it asks me to make a histogram. I don't have a lot of data to make this histogram, but I did build a set of bins, right? There are my bins, the low values and the high values. You'll notice there's no overlap, and all the bins have the same number of things in them. If I go to make a histogram, there are two distinct ways to make a histogram. One, through that insert charts. Up there on the ribbon, you'll see two different kinds of things that have columns in them. In the ribbon up here at the top, the upper left one says columns. But the one in the middle row, where all the columns are the same color, that actually says histogram. And if I highlight that, I can create a histogram. More on the other variations here next semester in the stats class. But that doesn't give me very much control. If I go to create the histogram using that, it'll decide the bins for me. I already decided bins. Instead of using the recommended chart version, I'm going to go to the data tab. And all the way over here on the right, there's a thing that says data analysis. When I click that, it gives me a list of things it can do for me. One of those things is a histogram. Click. And if I say, I want a histogram, it'll ask me, first, where's the data? And second, where are the bins? It even says right there, bin range. You need to give it the upper limits, not the lower limits for the bins. And then it can create both a frequency distribution based on these bins and the histogram chart itself. I'm going to tell it to give me a chart output by checking that lowest bottom box. It can also sort histograms. That's a Pareto chart. It can give me a cumulative behavior as well. That's called an ogive. You're never going to use that term again until next semester. And you can put it on a new page. So I click OK. And what do I see? I see there were 3 things in the first bin, 1 in the second, 1 in the third. Here's my histogram. There's a category that's labeled more. If I don't like that category, and I delete it from there, it deletes the category off the axis. It doesn't remove the excess part of the axis, but it removes the category. In the exam grade example, rather than writing 90 to 100, I usually write 90 and up. If there are scores up there, that's worth noting. But now I have both the frequency table and the histogram, and I can get that. Is this data skewed? Yes. Which way? Because the longer tail from our middle, our high peaks, goes off to the right. This is right skew data. I should check that. So I can go back to the actual numbers and ask, what is the skew of this data? If this is right skewed, what value should I get here? What sign? It should be positive. Yes, right skewed. I much prefer using the data analysis version of a histogram than using the automatically generated one. It is also possible to do this in a command line format. You can create the frequency distribution with a command equals frequency. And if you click on that, it'll show you all the things you need to list. You can either put a list of the bins as cells, or you can put a list of the bins in the command. I like the data analysis version because it does both automatically. I don't have to then subsequently create the bar chart. It's done. You should, between now and Thursday, go through and do all of these to make sure you can get this information. I will see you all on Thursday. Have a wonderful rest of your day. If you came in late, please make sure you found the sign-in sheet wherever it happens to be. It's in the back. So if you came in late, please sign in and then somebody bring that up to me. I will see you all on Thursday.